Good morning, everybody, and welcome to another fine webinar brought to you by the Lighting Design Lab and Seattle City Light. This morning, we are fortunate to have the second in the commercial heat pump water heating engineering deep dive series. You will be with Trevor Davis, who is with DNR International. He will be moderating this morning, and Colin Grist from Ecosire will be presenting. I'm Sean Dara, signing off for the lab. Have a good couple of hours.
Yes, thank you everyone. Thanks, Sean, for the introduction, and thank you all for joining us here this morning. My name is Trevor Davis. Like you said, I'm with DNR International, and Colin Grist will be our presenter today. Just a few things to note for maybe some of you who had not attended the first session. If you're looking at your GoToWebinar here, you can actually pull out the questions tab there, and that's how we're going to primarily communicate via this webinar. So if you can just type your questions in there, and we have quite a few spots throughout the presentations that we're going to stop and address those questions as they come in. If you have any issues with the audio, you can also drop down that audio tab, and there's a call-in number, so you can use that feature as well if you're having any kind of issues. And if you have any other issues throughout the presentation, please use the chat feature. If you have any kind of general sort of IT issues, use that, and we can help address as we progress through. Just as a note too, we will have the recording of this training along with the slides available on the Lighting Designs Lab page a few days after this training concludes. I think that's about all from me. I'll just hand it off to you, Colin. Thank you all very much for joining us.
Thanks, Trevor, and thanks to all of you for joining us, of course, again. We have part 2 of the engineering deep dive, where we're talking about commercial heat pump water heating systems. I think most of you hopefully likely attended part 1, where we discussed the 4 components of a heat pump water heating system and why you might be interested in that type of system to save energy in the building you're working on. Today, we're going to explore a case study of the Jackson Apartments, a new multifamily building in the Seattle area. We're going to dive into some key design considerations for all commercial heat pump water heating systems. Then we're going to talk about how to size effectively and efficiently using the Ecosizer, a free online tool to help you size heat pump water heating systems for multifamily buildings. And then we're going to also look at refrigerant and equipment selection, and some things to be aware of when you're specifying a heat pump is definitely what refrigerant that heat pump uses. And so we're going to talk about the varying qualities between the 3 primary refrigerants, R410A, R134A, and R744, which is CO2. So without further ado, we're going to jump right into case study after we do a Slido. And I introduced this in the first series or session of this webinar, but this is a free tool or free way for us to communicate with you. They don't track any information, and you can go to slido.com and then enter the code, and it's very similar to last time, but with a 2 instead of 1. So commercial heat pump water heater 2. There's also a QR code here, so you can just scan that and not bother yourself with typing in slido.com on your web browser. And our introductory survey is pretty similar to last time, where we're just asking where you're from, trying to get some feedback on who is in the audience today, as this is still a virtual classroom. Hopefully in a year or another month or 2, we can be back in the real classroom doing some of these more in person. But right now we're stuck to this virtual classroom, and this is a great way for us to communicate with you and to get some feedback on the presentation. Later on, we have an exit survey that's under the Slido platform, and then early on here to get some information about you and your experience with heat pump water heaters and where you're joining us from today. Montlake Terrace, Washington, great, local to the Seattle area. And I know we have more than one person in the audience. Any people from afar, Midwesterners or East Coasters? Occasionally we have some folks from Vermont or New York joining, where they have some great efficiency programs, and this is really applicable to those areas as well, as it is to Seattle.
Oh, I'll just note too, Colin, it looks like the number is actually the 809-109, a number, not C. I think that got changed by accident. So if anyone's trying to access, please use 809-109 for the session number. Apologies.
Thanks, Trevor. I did not notice that was different.
Yeah, let's change this on it. I will say too, while Colin is progressing through the slides, that Slido will automatically update. So if you just want to keep it open, on your phone or another browser, that we don't have to navigate every time, it'll just change automatically as we progress through. But thanks for everyone hopping on there.
Welcome from Denver. I was actually just in Denver a couple weeks ago. Great city there. And heat pumps will work, especially heat pump water heaters. New York, welcome. Awesome. We got some East Coast folks. Salt Lake City, Utah. That's fantastic. I was in Park City recently as well. Great area of the country there. Very beautiful. I think Park City just got some snow, so winter has arrived. Vashon Island, nice. Pacific Islander. And we got a question on what's your understanding of commercial heat pump water heating systems. A lot of us are in the intermediate range. It's definitely true when I speak to a lot of people in the field, a lot of plumbing contractors or other engineers. They know about it, but they might not have installed a system before, and so there's still a lot of unfamiliarity with the type of equipment they're working with. Got some novice and a couple experts. Thanks for joining, experts. What questions do you bring with you today? We had a lot of great questions last time. I'm sure we'll have another handful of great questions today. Options for heat stream you're pulling from ambient exhaust. Yes. So we're talking about heat pump water heaters, and they're extracting heat from the air and putting that heat into water. So where do we have excess sources of heat, and can we extract from those? Electrical rooms, casino floors, IT closets, those typically are generating heat and need a cooling system. Kitchens, so that's a great place to extract heat from, and I hope that we can touch on a few of those today. Appropriate utility incentives for heat pump water heating, how to design them. Yeah, I'm usually on the receiving end of those incentives, or helping people receive those incentives. But I think it would be great if you looked at the Advanced Water Heating Spec 8.0. That's going to be a great way to base incentives on, as the Advanced Water Heating Spec is currently available for residential systems, but 8.0 is going to be have commercial systems in there, and they're going to rank those systems and create a qualified product list so that you, as the person handing out incentives, can go to a tier 1 system and give them $100, give them $200 for a tier 2, or something like that. So I would encourage you to look at that Advanced Water Heating Spec. It's on NEA's website, if you're familiar with them. Sizing, quantity of hot water, absolutely. We're going to show you how to use the Ecosizing program or online tool towards the end of the session, and it's a really slick tool that a bunch of clever engineers at Ecotope created, and so I'd highly encourage you to use that for sizing of these systems. Return on investment of 7 years, expected life cycle probably 7 to 10 years. No, I would anticipate a much longer life cycle than 7 to 10 years. Some of these maybe earlier heat pump systems that didn't have as advanced technologies or weren't utilizing some of the more advanced control features we see today in the heat pump water heaters out there, those might have lasted that long, but we're seeing the heat pump systems last significantly longer than 7 to 10 years. And that return on investment was 7 years for a retrofit building. So we might actually see that shorter return on investment for a new construction. Manufacturers, yeah, we'll touch on heat pump water heater manufacturers. And we're going to touch a little bit on local codes, but we have other presentations where we dive more into depth on those. And so we're not going to have a ton of information on local codes today. So I think we're going to have some great questions. We'll try to get those answered throughout the presentation. And Trevor always does a great job at asking me the pertinent ones when we're going through this. But first, we're going to start with Jackson Apartments and a case study on this. People always ask me, you know, they've heard about heat pumps, they've seen, you know, conceptual image or diagrams to get those into your buildings and everything, but can we show them a real life example, a case study that's proven to be operating efficiently and effectively serving the building's domestic hot water load? So Jackson Apartments is a newly constructed multifamily building in the Seattle area. It actually has 2 wings, an east and a west wing. Total, there are about 532 apartment units. So a very big building, at least big for the buildings that I typically work on. It is a 7-story building, basically 5 or 6 floors above grade and a handful of underground parking floors. It's, you know, in Seattle, so everything's built on a hill. So we do have some exposed or kind of 6 stories on one side and 5 on the other deal. And it's a mid-rise multifamily building. So it's serving, you know, wide range of people, both families, students, low-income tenants. It's serving everyone or a wide range of folks, both in the studio apartment size to 1-bedroom, 2-bedroom, and there's some 3-bedrooms there as well. And because there's an east and a west wing, we put 2 central heat pump water heating systems in. One to serve the east and one to serve the west. We also did that because it was a large building and we had a bunch of earthquake expansion joints. And so we wanted to keep those distribution systems, or ideally prevent them from crossing that expansion joint, because crossing it just adds money to the project. And so it was early on in design, we discussed keeping essentially those 2 systems separated and decoupled. And it's in Seattle, Washington. So we located the system in the garage, and we'll talk about why we put it down there. The available products to us when we were designing this heat pump water heating system were essentially all across the board here, with the exception of this Mitsubishi. This was not on the market yet when we were designing this system. So we looked at using these smaller unitary heat pump water heaters, but unless we were going to do one heat pump water heater for a group of 5 apartments or something like that, there would be, you know, numerous of these systems throughout that 500-unit apartment building, tons of maintenance points to for the maintenance personnel to maintain in the building. And so we weren't really interested in using these smaller residential products just because of the sheer size of this building. And that goes for the Sandin or Sandco 2 heat pump water heater too. This is a 1.25 ton unit. So we could have done what we did at HopeWorks, which was a handful of clustered heat pump water heating systems, central systems. But for this size of the building, we would have had at least 30 of those systems, which would be in tons of maintenance points for those maintenance personnel. And so we decided not to do that. And we were looking at the bigger capacity heat pump water heaters, because this Mitsubishi, which is CO2, also larger capacity, wasn't available at the time during the design phases. And so we were looking at Colmac and Nile, and we had worked with Colmac recently in the past on another project, And so we decided to stick with them as the manufacturer of the heat pump water heater. And Colmac heat pump water heaters can be configured in either single pass or a multi-pass heat pump heating cycle, like we discussed in session 1. Single pass making the water hot with a single pass through that heat pump. Multi-pass typically taking multiple passes of the water through the heat pump to heat it from 50 degrees all the way up to the usable storage temperature closer to 120 or above. But one thing with these two heat pump water heaters is that they use R134A as the refrigerant. And that refrigerant is challenged by low ambient air temperatures. Specifically, once you get below about 40 degrees Fahrenheit, maybe 35 for these newer units, they start losing capacity significantly, and they don't really work at all, or they can't move any heat below that 35 degree Fahrenheit metric number. And so we had to get clever. And that's one of the reasons why we located it in an underground enclosed parking garage. You can see our heat pump water heaters are these blue cylinders shown in this conceptual architectural drawing, and we have our storage tanks there. And by locating them in an enclosed underground parking structure that's ventilated, we're able to have that ground contact buffer the air. And so for at least 10 years now, we've put temperature sensors in garages throughout the Seattle and Pacific Northwest region and measured those temperatures over the course of a year, or many years actually, to determine what's the lowest temperature we regularly see. And we see the outdoor air drop below 25, sometimes down to 23, even cooler recently. But in the garages, we typically don't see it drop below about 40 to 45 degrees Fahrenheit. And that's above the minimum temperature for those R134A heat pumps. So it's a great area, or it's a great opportunity to locate those heat pump water heaters in that enclosed parking garage to take effect of that geothermal energy that we're getting from our ground contact into the garage. And we also do capture some heat from cars. Cars get hot when they run. People are typically driving them into the garage, not pushing them. So those engines are on, creating heat. So when they park, there's a little bit of residual energy we actually get from those cars, which is another pretty neat thing that we weren't really considering early on. But for the most part, if we locate these one story down, or maybe at the far end from the garage entrance ramp, we can allow that 25 or 23 degree cool air on our design day to warm up as it gets pulled through that ventilated garage before it makes it to our heat pump water heaters, so that by the time that air makes it to those heat pump water heaters, it's above their minimum temperature, and those heat pumps can heat or provide heat to the water even when it's 23 degrees outside in Seattle. And this is true for most maritime climates. It's not just Seattle. Portland, this will probably work well too. I know that it gets a little bit cooler there in the winter because you're not as close to the sound or the ocean. But this can be a really great strategy, especially because a lot of these multifamily buildings already have a parking garage, and there's typically empty corners, often low down, that we can use to put this heat pump water heating equipment. So here's the floor plan of our east heat pump water heating room. And we have a handful of storage tanks, a temperature maintenance storage tank, our primary heat pumps. And then because this is in Seattle and the ambient air temperature is pretty low, the developer did want to have a backup system. And so we have a electric water heater that has a high capacity to it, high capacity water heater. And we also did include electric resistance elements in the temperature maintenance storage tank. So essentially that's another water heater, but we kept those element set points lower than the heat pump set point, so that the heat pump is always running first, and hopefully those electric resistance elements aren't coming on. So this room was a little bit too small when we first started working with the architectural team in the schematic design phases. So we just asked them to increase the room size. We actually took some of this area over here. I believe that's from electrical or fire protection, but they ended up having totally adequate amount of space. So that worked out well. And it's in a ventilated enclosed parking garage. So we have garage exhaust fans that are running continuous, and then those are peaking to a higher flow rate on detection of CO2 or CO or NO2 in the space. And we have about 26 square feet of exhaust louver right there, split between the two heat pumps, and 36 square feet of intake air louver that's being pulled through the door. Typically, we want our makeup air path to be flowing around 400 feet per minute as the design air velocity, and our exhaust terminals can go a little bit faster than that. We just want to be conscious about the noise through those exhaust terminals. And what you can't see here is there's a garage exhaust fan system sitting right about here. So as we're drawing air from levels above, it gets warmed up, then it enters through these ventilated double doors. They're just essentially chain link doors. It gets drawn into that heat pump. The heat pump extracts the heat, puts it into our storage tanks, and then we blow that cool air out back into the garage and direct it towards those large garage exhaust fans, which are running continuous and then peak into a higher flow rate based on toxic gases in the garage. And this has worked really well, operated last year, even during the snowstorm. We were moving heat into that water with our heat pump water heaters. So one or another very successful story here. We've implemented this design approach in at least 10 Seattle buildings, and all of them have operated well and smoothly, with a few exceptions that were easily corrected later on. And then I did mention that we have a full electric backup. And so sometimes I get asked how much, electricity or what's the load we have to plan for, because electricians might not be very familiar with this heat pump technology. And so it's helpful for them to get a rule of thumb or baseline kind of estimation. And so with electric backup, we're going to see about 540 watts per apartment for this type of system design. Without electric backup, we're going to see a much lower rate, because now we have heat pumps, and those heat pumps are super energy efficient, so a much lower energy draw in general. And so that's coming out to about 190 watts per apartment for this system installation. And so here's the next few slides are just a few pictures of the heat pump water heating room. And yes, there's a lot of piping in here, and there's a handful of pieces of equipment, but I'll try to go through it to clear it all up for some of us. And so this system is designed with a dedicated temperature maintenance system, because it's a large multifamily building with a very large hot water distribution system. And so we provided 2 Colmac CXA 15, so 15-ton Colmac heat pump water heaters. And those are the primary heat pump water heaters that use R134A. And that's why we put them in this underground parking garage area. We also have a backup 36 kW electric water heater that's behind this heat pump there, tucked into that back corner. And 3 500-gallon storage tanks for a total of 1,500 gallons of primary storage. So those are those 3 tanks right there. And we have a dedicated temperature maintenance system, and that is this large electric resistance water heater that's basically acting as a big storage tank, and then it has that electric resistance element in it for backup in case there's an issue with those heat pump water heaters. And then connected to this is a Colmac CXV, that's a 5-ton heat pump water heater. And it uses the refrigerant R410A, which can operate at lower ambient air temperatures. but is typically a little bit less efficient and also has a higher global warming potential. And we'll discuss global warming potential towards the end of this session today. And then, like I mentioned, this is a water heater, so there's a backup or an element in there that we're using as backup. So shown here, those are our two primary heaters. We're drawing air in through this ventilated garage or this ventilated double door. That air is being drawn to the backside of these heat pump water heaters where there's a blue filter. There's a dirty one that's on the floor. And the air is being drawn through that filter, through the evaporator. The heat pump's going to extract that heat, and then we're discharging that cool exhaust air out of this space. If we didn't discharge that air out of this space, these heat pumps move around, 6,000 cubic feet per minute or CFM during operation. So that's a lot of air that's being moved. And so we would actively cool this space down because that air would be short cycled. So we need to duct it out. That's one of the important designs of these heat pump water heating systems, is getting that cool air away from those heat pumps. And then here I said we had a dedicated temperature maintenance storage tank and dedicated temperature maintenance multi-pass heat pump. So there's our storage tank and there's our heat pump. I apologize for this kind of dark corner here. Sometimes hard to get good pictures in mechanical rooms and garages without a good set of lights. And this is a CXV. It uses 410A refrigerants, and we located it outside of the room because this fan is on a hinged door. And so if we ducted the exhaust from this fan out of the room like we did for those two primary heat pump water heaters, we'd have to come up with some solution to disconnect that ducting to open this face so that someone can service the interior components of that heat pump water heater. So we knew that this one uses 410A, it can work down at cooler temperatures, so we're not as concerned about those low ambient air conditions. And because we originally designed it with another CXA, or actually the HPA, Colmac's previous version of our 134A heat pump water heater, during the construction administration phase, the manufacturer approached us and said, hey, we got updated products. They've addressed a lot of these concerns and issues you guys have noted in the past. We were super happy about that. Manufacturers listening to us, they're making their product better, continuous improvement, always a good story. But one of the issues just with this heat pump itself is it was more challenging to duct than what we had originally designed for. And so we located that heat pump just outside that room for that reason. And it's been operating fairly well in that arrangement and regard. And we also have a control system here, and we're using a third-party control system because we're tracking the energy efficiency or the energy performance of this system, as well as a few other things. Like email alarms, routine maintenance calls, and just overall health checkups on the system that third-party controller allows. It can communicate with the internal Colmac controls, so we can actually extract a lot of data from that heat pump, from that Colmac heat pump, and look at it remotely on the cloud. And so that control system was also located in that room, and it's controlling everything. So it's both managing the primary heaters, what temperatures they're staging on and off at, and how many are coming on at once, and the delay of those or the minimum runtime. It's also turning on and off the temperature maintenance heat pump, as well as that backup electrical element. It's controlling the other backup equipment too, which is that water heater, and there's a pump to circulate water through that water heater. And then the other huge benefit is this sends out alarms and notifications. So we installed some of the first CXA Colmac heat pumps here. We have used the previous generation of HPA heat pumps in many projects throughout Seattle and Washington State, but during the commissioning phases or the construction administration phases, excuse me, The manufacturer had this newer technology available, and so we wanted to use that. And it turns out that there's some great advantages to using that newer equipment, of course. And so this whole system is trending data, like I said, and really a robust and reliable control system, as we can do health checkups on the system and also trend system performance and make sure everything's looking like it's running and operating smoothly. And so our bird's eye review of this system, we have our commercial heat pump water heating system. It's comprised of our heat pump water heaters. So here we got those two Colmacs. They're sized to meet the domestic hot water load for about close to 200 units of this 500 unit apartment building. And they're using R134A. So we put them in that enclosed parking garage that's ventilated because we're in Seattle and it gets cooler than 35 degrees Fahrenheit. We also have our primary storage, and we coupled those in series to provide a very essentially tall storage tank with a high level of thermal stratification and really high effective storage volume. We're making full use of the water volumes we have there at Jackson Apartments. And then we have our temperature maintenance system. We definitely have a hot water circulation system here, and it's a very large one. So we looked at using and designed in a parallel loop tank with a multi-pass heat pump water heater coupled to that. And then the last thing we had was, a control system. Here's that third-party control system on the wall, and there's the internal control panel for the Colmac. So we're using that third party to control all of the pieces of this entire commercial heat pump water heating system. But it is also interfacing with those internal controls of the Colmac, which is a great feature. So pausing for questions here on the Jackson apartment case study.
Yeah, thanks, Colin, and we definitely got some great questions here. I think the first one we had was just like sort of a clarification. The original slide you showed where it had the different manufacturers, there was the Rheem one that was said it was, I think, less than 1 ton. I just want to confirm, was it greater than 1 ton or less than 1 ton for that unit? Do you know for the Rheem?
I think that's about 1 ton of heat pump heat capacity, and then there's electric resistance elements in there, so it's actually a little bit more in total heat capacity.
Perfect. And so yeah, I guess on that too, someone's asking, are like these commercial heat pump water heaters like typically rated in terms of ton, and is this the tonnage of the cooling side?
So this is, great question. Typically we talk a lot about tonnage specifically for cooling, but tonnage is 12,000 BTUs per hour. A little bit easier to say than 12,000 BTUs per hour, 1 ton. So that's why I'm using it here, but this is the heating capacity for all these. Today, there are heat pumps that can make water, but those heat pumps might not be rated for domestic applications or potable water. And so we're focused today and in most of my presentations on those systems which we can use in domestic applications without a third-party heat exchanger. And so there are heat pumps available for space conditioning, right? Making hot water for a radiant system. But today we're really focused on the heat pumps for domestic hot water.
Got it. I know you definitely went through this a little bit, but sort of like the ventilation, is there like sort of a rule of thumb for like typically sizing for an enclosed water heating room, like in a parking garage? This one obviously you had to have the door with the slats. Is there sort of any sort of rule of thumb or anything that you guys can point to say this is how you should normally size that room to make sure that it has proper ventilation?
Yeah, so when the heat pumps are on, they're gonna pull in air and discharge it out. And so if you connect the discharge to the exterior of the room, then we're gonna be pushing air out, which is going to create a negative pressure in the room, or a slight negative pressure, which will pull air into the room. And that's our makeup area opening. So we're not essentially ducting or forcing the air in, we're just letting it passively come into the room and then making the heat pumps force that air out of the room. That's probably the most cost-effective way to utilize the fans and equipment available with these commercial heat pump water heating systems. But to do that, we want our air flow rate on the makeup air side to be pretty slow. We want the air to be moving slowly here because these fans don't have that much external static pressure that they can push against. And so that's why we're typically sizing that opening at a slower velocity that the air moves.
Got it. That makes sense. I know we got a lot of great questions here. The one I think I'll take do 2 more here before we. No, Colin, sorry, you still with us? We have audio issues or maybe not.
I mean, 100 feet per minute is a good.
Oh, sorry. I'm not sure. Colin, can you hear me? Maybe losing some bandwidth there. Oh, sorry. Sorry about that. Give us 1 second. Get us tee back up here. Just the.
Oh, Trevor, you back?
Yeah. Sorry. Can you hear me?
Yes. Sorry, I think I lost internet connection there. I apologize.
No problem. Sorry. Yeah, I think. Okay. Yeah, no problem.
I'm gonna turn off my webcam just because that's what GoTo suggested, but apparently there's a network quality issue that's been reestablished, which is good news for all of us.
Great. I can turn mine off too if that also helps. We can just do audio from here on out rather just save that. Okay, I'll just do just a couple more here and then we can sort of move on. I know we had a lot of great questions, so thanks all for dropping those in there. One of the ones that I think it's sort of an interesting question was in what situation, I know specifically when we're talking about that system, when would you ever see a situation, or have you seen one where that electric resistances had to kick on? Has that become an issue, or have you seen that in this application?
Absolutely. So we have seen, especially at this building, that this electric resistance kicked on, which does significantly decrease the system efficiency. However, it's very infrequent, and typically one of the issues has been a control glitch in the heat pump water heater itself that was corrected by the manufacturer with a service update or control service update. But primarily those are kept off. And we also saw that the 410A CXV had a manufacturing issue with the evaporator in that unit, which caused the unit to fail completely. And so we had to get that evaporator replaced. But in that time, when there's service being done to it, the system was running off that large water heater 3, which was serving the temperature maintenance hot water circulation load. So there's reasons to have backup in there. There's always, or backup or redundancy. If you're not doing backup, I would highly recommend that you put an extra heat pump in so that one can be down when and the others can be providing heat to the system.
Got it. Yeah, definitely. Thanks. A lot of other great questions. One was just specifically on the Jackson. I know we have a bunch there, and we'll get these at probably the next break. But what was the lowest temperature you saw in the Jackson parking garage? And sort of on that too, you had talked about blowing the cold air. Did you see a sort of a decrease in the overall temperature of that parking garage from blowing that cold air out? Was it affecting the overall temperature inside the garage?
So we're blowing the cool air out here, and our temperature, or our ambient air temperature sensors are in this room. And I believe the lowest we saw in this room was about 43 degrees Fahrenheit. And that's pretty typical throughout all of Seattle. or most of the enclosed parking garages in Seattle. If we can get these heat pumps a good distance from that garage door that's letting cars in and out of the garage, and a floor down in the building, we definitely see very steady temperatures, typically above 43 or 45 degrees Fahrenheit. If it's closer to that door, that's where we see more seasonal impacts for that temperature, for that ambient air temperature.
Got it. Makes sense. Thanks. And yeah, I see all the other questions in here. We'll grab some of those at the next break. But thank you all very much for all the questions. Thanks.
Great. So I hope that we showed you that the equipment that was available 10 years ago can be utilized to meet the domestic hot water load in Seattle multifamily buildings or Seattle area multifamily buildings. Even on our cool design days when it's cool outside and maybe snowing. The next thing we're gonna go into is a deep dive into the temperature maintenance system. Early on, about 10 years ago, with a lot of Ecodup's heat pump water heating systems, this was one of the most challenging aspects to make the system operate reliably, efficiently, and effectively at all times of the year. And so we're going to spend some time today talking about that temperature maintenance system and some solutions that we came up with at Ecotope to have it be a very robust system that is reliable and efficient. And so it's good for us to understand the efficiency boundaries. Let me turn back on the laser pointer. We have our equipment COP. This is typically published in the manufacturer's submittal or specification sheet, and it's typically rated at maybe 1 or 2, sometimes a handful of air and water temperatures. So it's not necessarily telling us how efficient the whole system will be when there's multiple heat pumps and we're seeing the impact of the climate and the climate conditions on those heat pumps. We also have another efficiency boundary, and this is our primary plant COP. This is making cold water hot for the occupants to use. Nothing to do with the temperature maintenance or hot water circulation system. So we can maximize this efficiency by just providing cool water to those heat pumps and locating them in the warmest space we can find in the building, or in an area where we can extract warm air from, or the warmest air possible. We also have our temperature maintenance plant COP, and this takes into account the distribution losses in the building and of course the air temperatures that heat pump's operating at. And so we want to maximize the efficiency of this this temperature maintenance plant as well. So if we put an electric resistance element in this tank, and that electric resistance element is always running to reheat the temperature maintenance losses, we're gonna have a low temperature maintenance COP, and we might have a high systems or a primary plant COP because we have heat pumps there. So it's best if we can apply a temperature maintenance heat pump water heater, or do a clever design with the piping in that swing tank arrangement that we'll discuss a little bit more later today, so that we can maximize the efficiency of this temperature maintenance plant. Because what we're trying to get to is a high domestic hot water system COP. So looking at the system as a whole, not just looking at a given manufacturer's spec sheet and they publish a COP of 4. So that's what I'm going to put into my, energy code model or my lead model or whatever, my energy estimations for the client I'm working for. So it's really important that we consider what our domestic hot water system COP is. And I mentioned the advanced water heating spec 8.0 that's in draft form and going to be released here sometime next year, I think is the target, or possibly later this year. And that's looking at the domestic hot water system COP, because they understand that we want the highest efficient systems possible. And so we need to be focused on that rather than just looking at the equipment COP, because even though the manufacturer publishes that at maybe a system or equipment COP of 4, we're not going to see that in practice. And the folks creating that advanced water heating spec are really trying to get a real life efficiency metric, and that's that domestic hot water system COP. So we understand a little bit about our efficiency boundaries, and we're going to touch on the hot water distribution system and how that impacts our system efficiencies. So the first thing to consider is how large, how dramatic, how great are those losses in your hot water distribution system. If we have high losses, we're going to need to be more conscious about them when specifying our temperature maintenance system and the equipment that's reheating that water. So on the left, I have a single family home, and it's got, you know, a very small distribution system shown here. You probably have there's a sink there, so another pipe going there. And we have solar thermal on the roof, but this could be a heat pump water heater serving that storage tank. Same concept. We have a very small distribution system in this regard, so we don't have to be that aware of it or that conscious of it during our design. But typically in these larger multifamily buildings, we have numerous floors. Each one of these gray boxes is essentially a unit, apartment unit. And we have a large distribution piping system, typically comprised of a main that runs along level 1 or level 2, and then risers that go up to serve each one of those units. And in this example, these apartments all stack. But please raise your hand if you've been working with an architect and they've given you a building and all the apartments stack. I can't see your hands, but I'm sure that there weren't that many hands raised. We typically have variation in our apartment design, and that might mean that this unit and the unit above it don't stack on top of each other. That results in more risers typically, or more piping to serve that riser as it's going to jog as it goes up. So with these larger multifamily buildings with larger distribution systems and a lot of architectural freedom, we often see very large, you know, temperature maintenance, hot water circulation loads. So we have to be conscious, we have to be aware of that when we're designing to treat that load along with the primary heating load. And what this really does is it impacts our thermal stratification. Our tank gets very mixed if we take that hot water circulation return and just dump it into our storage tank, and then it goes back out into the building again. We want to eliminate that into our storage tank so that we get a very thermally stratified thermal storage tank. And what I mean by that is cool water on the bottom, small pocket typically, a thin transitional layer, and then a lot of hot usable water on top. This is making the most, this is making a very effective, or this is leading to a very high effective storage volume because we have a lot of water above the usable temperature. So we're using our storage tanks efficiently and effectively in this design with good thermal stratification. On the other hand, if we just plumb that return water back to the tank, it's typically coming in at about 10 degrees below what it went out at. So if we're going out at 120, it's coming back at 110. And it's going to operate nearly continuous in our multifamily buildings. So it's going to always be going through, and it's going to basically mix this tank up. And that's going to lead to a lower effective storage volume and poor thermal stratification as we have a very large transitional layer or mixed tank. So we want to have a very stratified tank so that we can increase or have the heat pump operating at the peak efficiency. And we can see how that temperature impacts the capacity, and our capacity is directly related to our efficiency because we're typically putting about the same amount of energy in. And so we see that warm entering water temperature impacts the amount of capacity we're getting out, and it does impact that equipment efficiency. So this is for a heat pump water heater with an outlet water temperature of 150 degrees Fahrenheit. And we see a handful of inlet water temperatures, and I have the 120 and the 45 highlighted. So if we pick one air temperature at 60 degrees, we see that we get 195 kBTU per hour out of our heat pump water heater at that low 45 degree inlet water temperature. Whereas when the inlet water temperature climbs, whether it's to 100 or 120 degrees, we're getting a lot less capacity into that heat pump, and we're typically putting the same amount of energy into it that we were up here. So we can maximize the efficiency of our heat pump water heaters by essentially using the full heat pump heat cycle, taking cool water and making it hot, and not taking warmish water and making it hot or operating on that upper end limit. We also see that warmer leaving water impacts the efficiency, and I'll show this in a later graph because here we only have one outlet water temperature at 150. But typically with all heat pump water heaters, regardless of the refrigerant, the hotter water you make or discharge out of the heat pump, the less efficient the heat pump will be. And so we want to make hot water at a temperature that makes sense. We don't always want to make it up to 150, especially if we're going out at 120. You do want to be conscious about Legionellas or Legionnaire's disease and Legionella, and storing water at a higher temperature is arguably better for that. But it doesn't necessarily mean it needs to be stored at 150 in all regards. And so our capacity impacts, right, limitations on the refrigerant and those lower ambient air temperatures, but water temperatures, both outgoing and incoming, also impact our capacity. So it's important that we understand what temperature ranges we're going to operate in, or how the sequence of operation for these heat pump water heating systems will be written and controlled. And then defrost effects, we'll talk about that a little bit later when we get to sizing, but these heat pumps typically need to defrost when the air gets cool, the ambient air gets cool. And so we need to take that into account because we're typically not generating heat or putting heat into those storage tanks when the heat pump's in defrost. So that's going to lower our capacity over the course of a day. So we can pause for questions here before we move on.
Awesome, yeah. Definitely have a bunch in here. Start here with the ones that are sort of more related to the recent stuff we just covered. Someone asked, is the hot water return typically 10 degrees Fahrenheit lower than the primary tank outlet, or 10 degrees Fahrenheit lower than the mix down or a POU delivery temp?
It's lower than the mixed outlet temperature from your thermostatic mixing valve.
Got it. And then someone else asked, can you tie the return water to the cold water to still allow for stratification?
You can tie it to the cold water, but it doesn't help in your stratification because we actually end up mixing more of the tank. If we essentially took this pipe and connected it here, then we'd pull that yellow down further. We'd have warmish water at the bottom of our tank. We'd still be pushing water in here, and therefore it's got to go out, and it's going to go out here. So that's our mixed area.
Got it. We had a few too that were back from Jackson that I thought would be maybe good just to briefly touch on. A lot of them were sort of related to the controls. And one of the ones someone had kind of asked, like, you know, what was the equipment used for the controls, but also was what was the like sort of additional equipment for that one that was able to like track the efficiency of the heat pump water heaters? Or were you using controls like to track the units individually, or was it a whole plant? And then basically after like you looked at the data from those sort of controls and from that equipment, was the fully redundant system like needed? I know you talked about having one that could fully one. Is what was sort of the findings from that, the controls and the readouts from that information?
Yeah, that's a great question. So we did add equipment to get that third-party control system. There's some kind of brain or third-party controller, right? But we did also specify more temperature sensors than we needed to control the heating cycle of the heat pump, because we wanted to look at the outlet water temperature here, the outlet water temperature here. We could get the water temperatures from the Colmac heat pumps through their control system, but also look at this and then look at those electrical elements and whether they're on or off that are providing backup to the system. And we also were trying to, or we are and are continuing today to calculate the domestic hot water system COP, and then the primary COP, as well as the temperature maintenance coefficient of performance, or COP. And so to do that, we need to understand the temperatures and the flow rate into those systems. And so along with those additional temperature sensors, we do also have some flow meters that are trending how much water flow is going through these circulation, or the circulation path, or how much makeup cool water is coming in. And so that allows us to break out the efficiencies down to the equipment efficiency. However, just for cost savings, instead of putting a flow meter on that heat pump and one on that heat pump, we just put one here to get a totalized of both the heat pumps there.
Got it. All right, and then I have another one here. What was the typical recirculation losses with apartments in the new apartments? And did you see any improvement from using Appendix M? I'm not sure. That one.
Yeah, fantastic. I don't know about Appendix M and the savings we're going to get there yet. Theoretically, we get an enormous amount of savings with that smaller distribution piping, but we haven't utilized that in a handful of buildings and trended data on that, and we don't have any reports on that out yet. But I know that I think some people on our team are working on that. But the typical hot water circulation loss rates in multifamily buildings, new multifamily buildings, range significantly. I've seen some at 40 watts per apartment unit, all the way up to 400 watts per apartment unit. Our typical range is closer to 75 to 90 watts per apartment. That's a good rule of thumb to base your system design off of right around 90 watts per apartment or 100 watts. Sometimes we see it in closer to 75, but we like to be conservative as engineers, of course. But it really comes down to how much of that piping is in unconditioned spaces like the garage. We're putting the heat pumps in the garage, which is beneficial for our 134A technologies. But if we're running a bunch of piping in the garage and it's our big main piping, the garage is typically a cooler environment, and so we're going to see more heat loss there. So we want to be, and we also have a lot of clamp supports in that area, so we want to make sure that those are thermal bridge free and not bridging to the concrete. So the amount of insulation on your piping, the size of that piping and its relationship to Appendix M, the location of that piping, whether it be in a conditioned space that's always 70 or an unconditioned space that's tracking closer to 50 degrees, all have a significant impact on the heat loss rates. And that's why we typically see them vary so much. Also, if you have a lot of stacked apartments in a very I-shaped building, that's going to be a lower total heat loss rate than maybe if you have a bunch of unstacked apartments or modulating apartments in an S-shaped building. that's going to be a more circuitous distribution system. So we are actually doing a temperature maintenance study, basically looking at a lot of the common design approaches for those systems to try to come up with some better metrics for estimating and anticipating the losses, because we see that there's such a significant impact on our system COP and how reliable this equipment operates.
Got it. Yeah, that definitely makes sense. And sort of just to piggyback on when you're talking about for the Jackson, that it was in a garage, the fact that it does have like you said, it's really not as exposed to those sort of seasonal changes. Do you find that have you found that the overall efficiency is less because it doesn't get like the higher temperatures to be able to work off of, or how does that affect the net?
Yeah, so during the hot days of the year, when it's 100 degrees in Seattle and we're all frustrated about that, it stays cool in those garages, but it's not that cool, especially because what I've seen a lot of is split system heat pumps for space conditioning, and the outdoor unit is located in that garage. And so it's when it's 100 degrees outside, the person in that apartment unit is operating their cooling, which means they're discharging heat from that outdoor unit into whatever space it's in. So if it's in the garage, we're discharging heat into that garage, and that's heating up the garage. And so with more of these split system heat pumps going into buildings, we're seeing that garage air temperature is actually increasing during those cooling periods. We also see that on the heating cycle is when, it's cold outside and we're heating with our heat pump, space conditioning heat pump, that we're extracting heat from that garage, and our heat pumps are too. But typically in these large garages with a lot of garage contact or ground contact, we don't see as significant of a temperature impact for that relationship between your space conditioning system and your water heating system.
Got it. Yeah, definitely makes sense. Awesome. Yeah, there's a few other here, but I think we'll just wait for the next break here. I want to make sure we get through all the materials. So thank you so much.
Yeah, and then I'm not sure I answered that person's question fully, but overall, because if we locate these R134A heat pumps in the parking garage, we can run them during the winter or those cooler times of the year. And that's much more advantageous for our overall system COP than the slight difference in temperature we get because it's in a cooler space in the garage during some time.
Yeah,
so in general, it's actually better to be able to provide heat to the system at all times of the year, even when it's cool outside.
Perfect. Awesome. Thanks.
All right. We got a lot more to cover, but a ton of great questions. I appreciate you all being an attentive audience today and being passionate about heat pump water heaters. So the next thing we're going to discuss is some piping configurations for our temperature maintenance systems. And I'm showing 4 here. We're going to talk about the dedicated temperature maintenance system with a parallel loop tank and a typically multi-pass heat pump water heater connected to it. We're also going to talk about a dedicated series swing tank system. And I showed those 2 in the session 1, but we're going to dive into a few more details about them. And then we're going to discuss a combined system. So what happens when we take the hot water circulation back to the primary storage? We're not going to have a dedicated temperature maintenance system in this example. Everything's combined, both those heat pumps and the storage in that regard. And then number 4 is not that common, but we can have commercial heat pump water heating system without a recirculation system. And you might be providing heat tape trace on that distribution piping to maintain temperature in that. And that's essentially an electric resistance temperature maintenance system. So we're going to start with number 1 because that seems most logical. And that's a dedicated heat pump water heating system connected by parallel piping. This is the Jackson Apartments piping design. And so we show here that there's a third-party controller, but this could be using the internal controls of our primary heat pumps and work just fine as well. So in this example, essentially our systems are separated and we have two dedicated systems. We have the cool water coming in, going to our storage tank. Our primary heat pumps are going to heat that water up and store it back in the primary storage tank. When anyone opens the tap or there's a draw in the system, there's going to be water that's leaving that primary storage tank, going to the hot side of the mixing valve, mixing with the cool water and the return circulation water, and going out at a tempered level, typically of 120 degrees Fahrenheit. Our temperature maintenance system is going to take the nearly continuously operating hot water circulation pump and put some of that water back through the mixing valve and put some of it back into the dedicated temperature maintenance tank. That temperature maintenance tank will be controlled on with an aquastat or some type of temperature sensor to the heat pump. And so that heat pump is going to be typically configured in multi-pass heating cycle so that we have an unmodulated flow rate through this unit, and we're just trying to put as much heat into it as we can through each pass. And so that heat pump is going to take in that, typically 110 degrees, 115 degree water towards the bottom of our tank. These are typically set to put about 10 degrees Fahrenheit of lift into that. And so it's going to come out 10 degrees warmer at either 120 or 125 into that tank. And we're going to operate that and keep the water in this tank, or at least the top portion of it, above our discharge water temperature of 120. And so these two systems work in parallel. It's a really reliable, robust system for our larger multifamily buildings. And the important thing to design into this system is this parallel connection. If we were to take this water to the bottom of this tank, like we do in our swing tank design, then we risk having the heat pump try to heat up really hot water, because this will be typically coming out at maybe 130 to 140 degrees. So if we took that in there, then our heat pump will get 130 to 140 degrees and try to put heat into it. But that's going to be a very challenging operational point and will probably result in a pressure issue and an error alarm in that heat pump. So it's important to have this parallel connection. I will note that this pipe is uncirculated because the circulation isn't going back to it. So during periods of low use or no use, like overnight, this water in this piping can cool down. And if that happens, then we might get a little bit of cold water on the hot side of our mixing valve. So if you have a large length of piping, it's often best to just dump it right into the top of this and allow a little buffer zone there with that volume. But make sure you're dumping it into the top and not the bottom, so that you don't have that control issue with your multi-pass temperature maintenance heat pump water heater. But I'm showing it this way just to get the kind of parallel arrangement across to you, our audience. So I showed this at Jackson Apartments. We've done this at Cypress Apartments, at Boutique Apartments, at Block 11 or Sitka, Stackhouse. There's tons of apartment buildings in Seattle that Ecotop's designed with this design. And this have been operating for the past 10+ years.
Colin, it sounds like your audio is cutting out just a little bit. Can you hear me? Sorry, just give a second here. Get reconnected. Hey, Colin, can you hear us?
Yeah.
Okay,
All
yeah,
right.
sorry, cut off there for a few seconds.
Really sorry about my audio connection, everyone. It's frustrating for me and for you when the internet doesn't work and we're all remote. So
Sound good now. Yep.
back to it. And I lose everything when I do this. So let me get this going. Bear with me. Okay. So we have our primary heat pumps, 2 of them, and our temperature maintenance heat pump. And you'll notice that they look very similar, our primary heat pump and our temperature maintenance. They're essentially the same piece of equipment. We just set the internal controls of that Colmac heat pump up a little bit differently so that one's in single pass with a modulated flow rate through it to always get 140-degree water discharging out of it. And the other one set up as a multi-pass with an unmodulated flow. We're just trying to put 10 degrees into that water through each cycle of that heat pump water heater. So although, you might think that a multi-pass heat pump and a single pass look differently, they often don't. And it's really just some internal control settings and sizing of those components in that cabinet we see there. So there's our primary storage. This is the Yesler 3 or Cypress apartments in the Yesler redevelopment area. And we essentially have 5 storage tanks in series. And that allows us for a larger thermal storage volume. The hot of the top is connected to the cold of the bottom, and that happens as we go down that line. Hottest tank at the end and coolest tank on this end. And then we typically heat up all the water in here. So there's hot water all the way back to there. And then let that system run. We use our thermal battery, so people are drawing water out. Cool water is coming into this tank, filling up. And as soon as it hits the second tank, we're going to turn that heating cycle back on and start recharging these tanks. And then we have our temperature maintenance storage tank, and that's the heat pump connected to it, and then a mixing valve. And I'm showing a larger built up thermostatic mixing valve here because we have a larger multifamily building. So there's actually 2 valves in parallel so that we get good control of our low and high end flow rates that we see depending on if a lot of people are using water or only a few. So we're going to talk about our dedicated series or swing tank system. And we call this a swing tank because this tank is designed to swing in temperature from about 140 to 120 degrees during normal operation. So here we once again have a dedicated system so we can draw a line down and essentially have that cold water go into one tank and the hot circulation go into another tank. Our primary heat pumps are doing the same exact thing. They're taking cool water in and making it hot. Same thing as they were doing with the dedicated parallel loop tank arrangement. And then our hot out from that primary, this is where it changes, is connected to the bottom so that we're mixing this tank. This is where we want a mixed tank or a poor thermal stratification because we're trying to use the overheated water to offset the losses in our distribution system. So when someone opens a hot water tap, we have cold water that flows into the bottom of the tank that pushes hot water out of the top. That water is in the swing tank design, needs to be close to 150 degrees Fahrenheit because we want it to be as far above 120 degrees Fahrenheit so that we have overheated water and essentially overheated energy that we're or extra energy that we're transferring into our swing tank. So we get a flush of 150 degree water because Suzanne took a shower and we get our constant recirculation pump flow rate. That's probably a lower flow rate than Suzanne and a bunch of other people showering her is typically lower. So those two streams mix together, that maybe 110 degree water and that 150, and so that keeps it above about 125 degree Fahrenheit. And so during a lot of use, we're getting a lot of energy transfer, and so this tank is often around 140 degrees Fahrenheit, or 10 degrees below what it's coming out here. And then during no use or low use, the temperature in this tank drifts down because we're not getting as much energy from that primary storage tank. And so the temperature swings down, and the key is to make the volume big enough of this tank so that you can swing through your longest duration, which is typically 4 to 6 hours overnight. And the Ecosizer tool that I'll introduce here momentarily has ways to calculate the volume that you need here to make the best use of that swing effect. And so if we get a lot of swing in our tank and it drops below 125, that's when our electric resistance element will come on and heat that water up inefficiently. So we want to design for that not to happen. And that's why we need a large volume there, so that we can have match that volume with essentially a longer duration of low use overnight. So our series swing tank, we're essentially connecting this primary storage in series with our temperature maintenance, just as if we were to have multiple primary storage tanks and we connect those in series. So hot to cold, and then again, hot to cold. So doing this, we needed to connect down there, right? If we go to the parallel, we're never going to transfer energy into that. And if we take it to the top, then we're going to only swing essentially this top upper portion of that tank. This can be a really, really efficient system design if we have low temperature maintenance or hot water circulation loss rates below 50 watts per apartment. So I said that, you know, we're typically between maybe 70 and 90 watts per apartment. We want to get that down to 50 watts per apartment to really make the best use out of this tank and to prevent that electric element from running. So this is better suited for small distribution systems, or to do multiple clustered central systems where you're just serving vertically in the building. You can use this on bigger buildings, but we're going to see a lower system coefficient of performance than we do with some of our smaller system designs. And then the other thing you want to be aware of is, can I make that overheated water efficiently in my primary storage tank? We'll see that R410A and R134A are more impacted by higher outlet water temperatures. Their equipment COP will be significantly reduced if we make 150 degree water compared to if we make 130 degree water. So we want to make 150 degree water with this swing tank design, and the CO2 or R744 heat pump water heaters are best suited for that. They are really efficient at making that 150 degree water so that we can really utilize the excess of energy in this tank when someone draws water out the tap. So these two systems are working in series, but they're essentially dedicated. We're not going to mix our primary storage and create issues with our primary heat pump water heaters because we're providing a dedicated path for that hot water circulation load and those losses. And this is the first one implemented, and this is at the Elizabeth James House apartment in the Seattle, Washington neighborhood of Capitol Hill. And we have 4 Sandco or Sandin heat pump water heaters. They used to be called Sandin, now they're Sandco 2 or Sand CO2. And these are coupled in parallel so that we're essentially getting one big heat pump water heater out of 4 of these connected in parallel, and there's stage 2 in and then the second 2. This has been a very efficient operating system because we have a smaller distribution system with low temperature maintenance losses, and its senior occupancy So there's a lot of use periodically throughout the day with less peak uses like we see in more of a mixed multifamily building. This was an existing building, a retrofit. It had electric resistance boilers and still does, or electric resistance water heaters. And so those were originally connected to these 3 tanks. We added a 4th tank and connected those to that tank, and then connected the heat pump water heaters to these primary storage tanks. And you can see that hot water coming out and going to the bottom here. And then our temperature maintenance is hot water circulation return is coming right here and also going to the bottom of that tank there. Here's our thermostatic mixing valve. It's a much smaller valve. So I showed a lot of larger valves for larger buildings, but these electronic mixers are also available in smaller sizes, and I would encourage the use of that type of thermostatic mixing valve, especially with swing tank systems, as the temperature on the hot side of this valve is designed to fluctuate in that system approach. And so we demonstrated this at Elizabeth James and then a handful of other projects, and the CO2 heat pump manufacturers absolutely loved it because it was mitigating potential issues for their equipment with that hot water circulation return. And so they are now designing these skid or packaged systems to take the burden off the designer's plate and really create a robust, reliable system that can be implemented and is really a plug and play application where you're just connecting 3 water pipes and probably electrical and maybe control wiring. So this is Mitsubishi Skid, and they're designing it to have 2 primary storage tanks, a temperature maintenance swing tank, and a primary heat pump water heater. And then there's some other valves, components, pumps, and the control system shown there. In Sandin, or now Sandco 2, is also developing this water drop product from Small Planet Supply, a local Seattle rep or Washington State rep. And that's using a bunch of Sandin small, about 1.25 ton or about 15,000 BTUs per hour heat pump water heaters. And then there's a cabinet there that has the storage tanks and all the piping. And they're designing this to be modular so that you can add another essentially cabinet. You get your first cabinet, it's got the control system and some mixing valve and other components. And then you're adding another cabinet, which adds storage and heat pumps. And so you can couple these together to really utilize this small residential product to serve bigger buildings, but without having a bunch of field piping work needed to be done. And it's still one central plant. So it's one maintenance point rather than multiple maintenance points, which can be advantageous for that maintenance contract personnel. So we demonstrated that this was a great system design, and the manufacturers are definitely jumping on board with this for their products so that we can get really highly efficient systems in these multifamily buildings or other buildings that we're working on. So here's another opportunity for questions. And I got about a half an hour left and still numerous slides. So
we'll
maybe if we don't have,
take a few, yeah. I'll just maybe take a couple here. One was just real quick, and I think this is another project we'd worked on, but the skids, those are used for existing, or have you seen them used in existing buildings? And I think that's Bayview, right? Don't they have a skid for an existing building? It's not always going to be new construction, right?
Yeah, so Bayview Apartments in Seattle just had this skid put in this past month. And commissioning was ongoing this week, so I don't have any results, but I feel like everything's going pretty smoothly on that project. You know, there's always challenges in a retrofit that come up. Anyone who's worked on one knows that. And then the Sandin water drop, I haven't designed one of these in yet, but I know that others have in California. And so these are new to the market, but I think there are some out there if you wanted to reach out to the representative and see if you can see a demonstration project in person.
Got it. Yeah, I'll just do one more here. Then someone's asking, with the R134A, how much of a difference is there in efficiency with a 90-degree lift versus a 10-degree lift, and basically kind of which one of those is more efficient?
Yeah, typically the 90-degree lift is more efficient. And it's just allowing the heat pump to use its full heat pump cycle, essentially, or capture more of that free heat available through the ambient air.
Got it. Yeah, I know we have a bunch more in there. Want to save those if we have some time at the end, or if we'll just follow up with you. But thank you all very much. Please feel free to keep dropping those in there and trying to address as many as we can. Thank you.
So here's our recap. Parallel with multipass, this is typically great for larger buildings with large distribution systems. In-series swing tank, really great system, but just make sure you first drive down the hot water circulation losses because that's going to impact how much this element engages. And then please utilize the Ecosizer tool to estimate the size of volume you need in this swing tank so that you can actually swing through those periods of low to no use, typically your 4 to 6 hours overnight. And so the next thing we'll introduce is combined. This is possible, but it comes with some risks and some considerations. So our combined system, right, we're just taking our hot water circulation return and we're dumping it back into our storage tank. This is common system approach for a gas or electric resistance water heater, except this would be typically taken lower in the tank all the way down there. You definitely want to take it below or put it into the tank below the 50% mark, because if you put it up here, your aquastat's typically down here, and so you're not gonna get that thermal on that you need, or it's not gonna read a temperature low enough to turn that on if it's just mixing up this tank. So this is kind of our all eggs in one basket approach, which is never the smartest approach, I think. You can make it work. It can be reliable. We see most of these system designs do have issues though. And those issues are primarily cycling of this heat pump, frequent cycling of it, which is not great for heat pumps or many mechanical devices. And then sizing issues. Our hot water circulation load is continuous all year long and typically a pretty low loss rate compared to our primary load. So we're seeing we need a lot of energy goes out when we have a draw in the system, and we're only losing a little bit through this, but it's all year long, so it adds up over the course of the year. So this is a periodic and high amount of energy that needs to go out when we have a primary system draw, and we have a lower, more continuous operation with the return water. So if we're sizing our heat pump with just one heat pump, it might cycle really quickly to reheat the circulation losses and then have a more appropriate cycle when we're heating for our primary load. So it's important to add staging to your design if you have a combined system so that you can better match, instead use 2 of these heat pumps or 3 of them instead of 1, so that you can better match and only bring on 1 heat pump to reheat that hot water circulation return losses, and then bring on the rest if you're doing your full primary heating load. So staging is critical in our combined system designs to really mitigate the cycling issues that are related to the difference in scale between our heat loads, whether there be temperature maintenance or primary heating, people actually using water. And then because this is taken into the tank, our primary tank, we typically lower the effective storage volume because we mix a bunch of warm water in that tank. So we're not making as efficient use of our hot water storage tanks, and we have to purchase those. And we're often trading the volume of those against heat capacity, which I'll show you when we get to the sizing section of this presentation. So lowering the effective storage volume is not great. And then we're also typically seeing warmer inlet water temperatures to our heat pump because now it's got to heat up this warmer water. And so that's going to lower the heat pump COP. And that's both in primary heating mode and temperature maintenance because it tends to be a very mixed tank. And then this is often technology dependent. The variable capacity heat pumps work much better than the single or fixed capacity heat pumps in this regard due to that differential between the two loads, our primary and our temperature maintenance loads, and just the internal controls. So how hot of water can I take into this heat pump? Some, that limitation might be 100 degrees Fahrenheit. Others, that might be up to 120 degrees Fahrenheit, but only when the ambient air is warm. So if I have 115 degree water or 110 coming back, that might be at the limit of the heat pump or very close to it. In some cases, it's going to be above it. And so it's technology dependent. You want to work with your manufacturer to determine the highest inlet water temperature you can operate this heat pump at. And that's going to be in relationship to your outlet water temperature and your air temperature that heat pump's operating in. So once again, this is possible. There's some risks, and that's why we primarily use dedicated systems, either utilizing that series tank. And then the fourth option is no recirculation. And this is not what our hot water distribution piping looks like, but conceptually what I'm trying to get across here is that this isn't that common because essentially we have to put this electrical element on all the distribution piping in the building. And some of that distribution piping is very challenging to access. And this heat tape or trace, I would encourage access to it. Not necessarily required, but good practice because it's an electrical element that might need to be replaced or changed at some point. So for smaller distribution systems, this might be an okay design approach, but it is just going to be electric resistant to the heat of those temperature maintenance losses. So we want to drive down those losses first so we don't have that much to reheat. And I don't think we see this that often in multifamily buildings. Someone correct me if I'm wrong in the Q&A portion, but this heat tape trace has been out there. We see it a lot for freeze protection on places, but not that often is it used to maintain temperature in our distribution piping. And of course, you'd want to insulate above this. A handful of these pictures I show don't have the insulation on the piping because we're trying to get a point across, and this is definitely one of those pictures. Oops. So pausing for questions here before we get into system sizing.
Yeah, we had just a couple here. One of the ones was asking about like why in that one system you're showing like why a constant flow for the recirculation pump. Basically saying, you could save 90% in pumping if you had it thermostatically controlled, and is it worth the extra pumping for the efficiency of the rest of the system?
Yeah, so if we can stop that pump, that helps. And the longer we can stop that pump, the more it reduces the associated losses because we're not circulating water during that period. However, in most multifamily buildings, people want hot water at all hours. And so with my experience, every time we put some kind of demand-based or
Oh, sorry, Colin, cutting out there just a little bit. Apologies, everyone. The joys of working remote.
Thermostat control works great, but basically demand-based pump sequence from the and ends up hot water, and that water heating system. I love the idea. You want to areas can be or door off, but they can be very challenging in our multifamily buildings where we have use throughout all hours of the day. And Ecotop studied that and seen that, yes, even though people use less water at 4 a.m. in the morning, there's still some people that get up and take their shower then. And so we need to have a, hot water available for them at that time. And so that's why those circulation pumps, I'd say, are nearly operating continuously, even when we have some kind of design approach to reduce those losses or stop that pump for periods of time.
Yeah, yes, it cut out just a little bit there, but I think we got the cut the tail end of it for that
Great.
one. So thanks.
Okay, hopefully I don't cut out anymore.
Yeah, no problem. I think yeah, and I'm trying to see here, go through these ones. Yeah, someone's asking too why the recirculation of the temperature maintenance tank was heated by a heat pump instead of a electric resistance. And basically is that circulation heat pump water heater like a different model than them, just sort of like the reasoning behind using that different system. Hello, Colin. Apologies again, everyone. Best there.
All right, sorry everyone, once again, I think I'm back.
No problem. I think maybe we can you want to just continue through, and then we can just grab some questions at the end here. I want to make sure we get through all the material. Still.
Yeah.
Colin, I will actually, let me try, I'll text you the call-in number. Maybe that would work better.
Let's do that.
Okay, I'll do that real quick. Give me a sec.
All right, am I back? Can you guys see the slides? All right, hopefully I'm back on air. Apologize once again. It says I have full internet, full bars. I don't know what's happening. So yeah, sincere apologies for us all, because our time is our most valuable asset, of course. We can trade off between our heat capacity and our storage volume, and that's one thing I want to highlight to us all.
Yeah.
Typically, gas water heating systems have been sized with a very low storage volume and a high heat capacity, because it's cheap to buy more gas heat capacity, right? It's just a flame burning, pretty simple. Heat capacity with heat pump water heaters, we're moving heat, and we have to size those compressors, that evaporator or condensers to move that heat. And so heat pump heat capacity is typically more expensive than our storage capacity. So to get the most economical system installation or a low first cost system, what I typically advise people is to look at larger storage volumes with less heat capacity than you have with your gas water heating system, which is typically sized for high heat capacity or a lot of flame and a lower storage volume or smaller barrel of water seen on the screen there. And so we need to size for the hot water load, that load profile, and the occupants in the building. That load profile changes depending on the use type. In most motels and hotels, we're going to have a high morning peak because that's when people use their showers. You get kicked out of that hotel room around noon, and not many people are cooking in their hotel room or doing laundry. So we typically see a lower use rate at the end of the day there. Multifamily, on the other hand, shown in this bigger image, right? We still have that morning peak because people are showering, but we also do have an evening peak where we're doing most of our cooking and cleaning, laundry and elsewhere. So it's really important that we understand our load and we can size the storage volume to coast through our peak load period instead of sizing it to recover within that peak load period like it is for gas. And so that we can trade off between heat capacity and storage volume and result in a lower first cost system design if we're prioritizing storage a little bit more than we did in a gas water heating system. So how do we do that? Well, there's the Ecosizer, which was created here at Ecotope. You can find it at ecosizer.ecotope.com. It's free, it's online, and I'll show you how to use it here, hopefully successfully without losing internet connection. So if you navigate to ecosizer.ecotope.com, you get to this home page. There's an 8-step little blurb on how to use this tool. There's also a glossary, which has a lot of great definitions and information in it. And then there's documentation on how this tool was built, who funded this tool, and what types of buildings and occupancies you can use it for. Now, this is just for multifamily building system sizing right now because we use that multifamily load profile to make this tool. We are working to incorporate other load profiles so that we can use this to size other building types like offices, schools, fire stations that are great applications for heat pump water heaters. But right now, it's only for multifamily. So the first thing you're going to do is just define the load or who you're serving in the building and the anticipated peak water use rate. So we can do that just by putting in the total people and the total apartments, or we can switch to this where we can pull from other sources to define our occupancy rate for a studio or occupancy rate for a 2-bedroom, and then define how much water they use. I'm going to keep it on total people and apartments for this example. And let's say we're serving 60 people in a 30-unit apartment building. And here we have a toggle bar where we can set it at the ASHRAE low. So that's pulling from our ASHRAE handbooks, or the ASHRAE medium at 49, what's pulling from our ASHRAE handbooks as well. The ASHRAE low tends to be fairly conservative, or liberal maybe. It's fairly low in the sizing, and the medium ASHRAE tends to be very conservatively sized. We typically don't see people using 40 gallons of water per day. We have our Ecotope market rate, which is my favorite point to size it, and that's assuming 25 gallons per person per day of hot water usage. The next thing we're going to define is our water temperatures. How cold is our water coming in? and the temperature of water going out to the building occupants. We're also going to define the storage temperature of that. Excuse me, I think I lost for a minute there. We can select how high that is in our tank and our storage efficiency. The next thing we're going to select is our temperature maintenance system design, and we have the swing tank, the parallel loop tank, which we went over, and the primary node recirculation. We're going to choose parallel loop tank because we went over that today. There is also at the end or the lower down on this page, load shift, and you can toggle that on and off to determine how much extra storage volume and heat capacity you'll need to essentially do load shifting to take better use of time of use pricing if you're in California where they have that, or maybe if Seattle in the future has time of use pricing, that's going to be super helpful for us all. Then we can click the button at the bottom, size your system. And that's going to give us our results. And so our results come here. This is what our system was sized for. You can see our recirculation loss was sized at 100 watts per apartment. You can change that in this program. And then we can use this toggle on the bottom to select various different storage tank capacities. So this would result in at least 232 gallons of primary storage and 63.8 kBTU of heat pump capacity. And that's going to mean that the compressor will run 13.7 hours during our design day. We can toggle this over and look at maybe more storage, which will reduce the amount of capacity we need. So now we need about 400 gallons of primary storage, 45 kBTU per hour. Instead, what was it previously? Close to 60 kBTU per hour. And that compressor is going to run for a longer time, so 19.5 hours. You want to be above this green bar, of course. If you're below it, you're not going to meet the load during the design day. This your results to PDF and put it in your company's, on your company's server. So really handy there for documenting your results. So hopefully that was a really brief introduction to that Ecosizer. We actually teach funded by and some more intricacies of how to use it for various occupancies and so forth. And then the last thing we're going to touch on is refrigerant and equipment selection. So now we know how big of a heat pump we need and how much storage, how big of a storage volume we need. But it's important that we understand how to actually select that equipment. And so we have a handful of heat pumps available out there today. Some of them are based with CO2 as the refrigerant. Others use R134A, 410A, and we have some small bad ones R135. That also use 134A.
Colin, looks like you're just cutting it out again.
It's important glowing potential and understand warming potential and its related.
Hey, Colin, I sent you the phone call number to them. Maybe a better option here to close out if it's possible.
Global
Apologies, folks. It was a bad connection here.
chipped pump. The refrigerant in these heat pumps, refrigerants has a global warming potential. CO2 is the basis of that scale, and the basis, so it's a global. This graph, which holds a fixed capacity potential or heat pumps, the higher the our environment for those spaced out, it's a big A in our packaged product. Is in the system. The water heat toxic refrigerant.
Oh, Colin,
it
sorry.
doesn't look like
Colin.
the slides.
Yeah.
So
yeah, we're
refrigerant talking about. I apologize.
Yeah, sorry, we're like catching like every other word. I sent you the phone number.
Catching up.
Try that? Yeah, we're catching like every other word. Could you try like the phone call number and then the pin maybe? Let's see, just to try and close it out. I know we missed that section. So make sure we got the information.
Yeah.
Yeah, apologies, folks. It's the challenges of working remote here. Once I can see, but Colin can call in and try and address some of the questions here. Yeah, and you should be able to have your pin, Colin, should be under the audio tab. So you should be able to the call in and the access code and then the audio pin, so you can go through that. And let me know if you need me to pull up. I can pull up the slides too and do it from my side if it's easier.
Hello? All right, I think everyone can hear me again.
Yep, you're much clearer now.
Great. All right, so global warming potential, it's important for our heat pump water heaters, but I would like to highlight that in these packaged commercial heat pump water heater products, we typically have a very low volume of this toxic refrigerant. So our VRF base conditioning systems, right? We have piping going through the entire building, carrying this refrigerant in it. There's a large volume, and we need to be very aware of it. It's great that in these heat pump water heating systems, we typically have packaged products that piping has been done in a factory rather than in a field like a VRF system. So our R744 is our CO2, and that's what the scale is based on, so that's a 1. We also have higher COPs typically with those CO2-based refrigerant systems than our R134A or our 410A, which you can see there. Now the 410A, there's a huge benefit because we can operate them down to low air temperatures, just like our CO2 refrigerants. But our R134A, right, they're challenged by that low air temperature. So please be aware of that in your system selection or the equipment selection for that heat pump water heating system.
And then we can see that we might get, or these are two heat capacity charts, one for an HPA15, that's a R134A heat pump water heater. And we see that it drops significantly with air temperature. Our entering air temperature is down here. And so although the manufacturer might rate our heat pump water heater at 70-degree air and maybe 120-degree leaving water temperature, which is somewhere between 250 and 270 MPH, at our actual design condition, we're going to be getting substantially less. So once you get that required heat capacity from the Ecosizer program, it's really important that you're sizing for the design day rather than sizing for the manufacturer's published point. And Trevor, I think the slides are still a little bit behind on the audience's end. We're coming to the end of this program. So I really apologize for this. And hopefully you can review these slides at the end on your own. During defrost is another thing we need to be conscious of, is these heat pumps aren't providing heat to the system. And so we need to be talking to our manufacturers, asking them how long that defrost cycle is anticipated to be, and then derate that capacity based on the duration of that defrost cycle. There's typically two ways to defrost a heat pump, active or passive. Active, the refrigeration circuit is essentially turned in reverse, or there's a bypass route established. And so we're using the hot gas to melt the ice that's on the evaporator coil. Passive only works when the ambient air is above 32 degrees Fahrenheit, because we're essentially operating a fan to move air across that oil to melt the ice on it. And that's typically a much slower, much longer and slower defrost cycle than an active cycle. And we have a few concluding slides on putting the pieces together. So I'll highlight, right, we have our four main components of our heat pump water heating system. We got our heat pump, which is our primary engine. We have our primary storage tank. We have a temperature maintenance system and a control system. And all of those pieces need to work together so that we have a very successful commercial heat pump water heating system installation. And I'll conclude there. Once again, sincerest apologies for the internet connection issues. We have more of these commercial heat pump water heater webinars coming up, both later this month and next month. So please go to the lightingdesignlab.com and the educational section of that, and keep up to date on those presentations. And I promise that we'll have a better, more reliable internet connection for those, even though it seems like that seems to be okay on my end, but periodically goes out.
Yeah, thanks, Colin, and thank you all for bearing with us. I know this is just one of the many challenges here of working remote and having having some tech issues. But thanks all for doing it. And yeah, just like Colin was saying, please remember this is the second of this one, but then we do have the design operations and maintenance coming up. So hope we can join us there. Colin, do you have a few minutes? I have a couple questions here. Did you want to go and wrap it up?
Yeah, no, I have a few minutes to go over questions.
Perfect. So someone asking, this was sort of in the original one, is like, what is the space requirement of a heat pump water heating system compared to like a traditional boiler system? Is there basically any general comparisons that you can have between the two?
Yeah, I would say between 30% and 50% more area.
It's just for like
more
the airflow, pretty much?
That would just be for the room size.
Room size. Okay. Our
heat pump water heater louvers and air terminals are much greater than our gas water heater flue exhaust and intake air opening.
Awesome. And this one too, we had a couple questions about the sort of the storage capacity and sort of the maintenance of that. So how would you determine, I know we talked about this a little bit throughout the presentation, but how would you determine the storage tank temperature and then sort of like also the sizing for that storage tank for a specific unit? Is that going to be based on sort of like usage, or what are the factors you're trying to look at when you're sizing that and also finding those set points for the storage tank?
So the primary storage tank set points, we typically set those between 135 and 140 degrees Fahrenheit. If we're doing a swing tank system, we set that at 150 degrees Fahrenheit. So we're trying to store water at 150, a much higher temperature. But for our R134A systems, we're typically storing water in those tanks right around 135 degrees Fahrenheit.
Got it. Did you know for the, this was someone had asked before, for Jackson, do you know like the annual COP for the primary heat pumps and then maybe like the COP for the whole system? Do you know those numbers offhand?
Not offhand for Jackson, but for Cypress Apartments, which is a very similar system that's using the later, more outdated Colmac technology, the HPA heat pump water heater rather than the CXA at Jackson. We're operating at a system COP of about 2.6 annually. So that's a 260% efficient over the course of a year. And that's that's the system COP. So it's taking into account the temperature maintenance and the primary plant COP. We typically see that primary plant COP closer to 3.0 and the temperature maintenance COP closer to 2.2 to 2.3, depending on how big the losses are in that building.
Got it. Yeah, we said one's coming here too. Where's the key difference where you install the swing tank in series versus parallel?
So the key difference really comes down to the primary heat pump water heater. With CO2 heat pump water heaters, we can make really efficient, or we can make overheated water very efficiently. And so with CO2 heat pump water heaters, swing tank design is a great design approach. And the key is to drive down the temperature maintenance distribution losses in that system design, which usually means smaller distribution systems or more insulation on the piping. If we have our larger buildings that are using maybe R134A heat pump technology, the parallel loop tank is a much more efficient design approach.
Got it. Yeah, I think that just about covers all the questions. If there's any last minute ones, please feel free to drop in there, and I apologize for the sirens. Yeah, I think that's about it. Again, thank you so much, Colin, for all the great information and for everyone dealing with us with the IT issues. And I hope we were able to provide you a lot of great information for this one. And as like I said before, the recording and the slides also will be available for you to view here in the next few days. And Colin does have up on the screen there, October 26th from 10 to 12 is going to be the first session of the design, operation, and maintenance, which is a great seminar. Really get into the details for these systems, and it's a 4-part series. I hope to see you all there for that. Colin, did you have any other kind of closing remarks? I think we could probably end it.
No, thanks everyone for joining us today, and look forward to working with any and all of you in the future.
Thanks. Thank you all very much. I hope you have a great rest of your Wednesday. Appreciate it.